Hello, everyone. Thank you for attending this talk. It's on joint channel coding of consecutive messages with heterogeneous decoding deadline in the finite block-length regime, which we recently submitted to IEEE Wireless Communication and Networking Conference. And it's a joint work with Malcolm Egan and Jean-Marie Gars. So as we know, the fifth generation of wireless networks have to accommodate three types of data communication. The first one is enhanced mobile broadband type of communication, which requires high rate, extended coverage, and high spectral efficiency. The second type is massive machine type communication, which is when there are too many devices connected to each other, each with battery lives more than 10 years. And the last one is ultra reliable low latency communications, where require low latency, high reliability, and high availability. They are aimed for critical missions and are the focus of this talk. So they have there are many applications based on ultra reliable low latency communication. You can see them in autonomous driving, remote surgery, remote management, and so on and so forth. So in this talk, the way that we are going to look at ultra reliable low latency communications is from an information theoretic point of view, meaning that here delay for us is at symbol level, meaning that we consider number of channel uses, and then we categorize the types of delays that we have into three categories. First is transmission delay, meaning that we cannot send packets over unlimited number of channel uses, so we will have a small size packets. There is a very well-known tool to take care of this type of delay, which is finite block-length information theory, which I will explain briefly later on what is the concept. Then we have encoding delay, where packets are with different arrival times. And we have also decoding delay, where packets are with different decoding deadlines. So to just motivate it, the last two categories, assume that we have a sensor, which is observing control packets periodically. So the question would be, if in the middle of the transmission of one packet, another packet arrives, what sensor should do? It's going to stop the transmission of the current packet and send the other one, or just tag the both together and jointly transmit both of the messages. So to answer this question, also we have to consider if there is a decoding deadline also at the receiver side. So there are, especially for URLLC packets that might be time sensitive, then each of them has to be decoded by a specific time at the receiver. So as a result, our focus here in this talk is the joint transmission of the packets with different arrival times and different decoding deadlines in the finite block-length regime. So first, I will explain what is the concept of finite block-length regime, which might be not very familiar, which might not be very familiar to everyone. So the famous Shannon Theory says that if we have given sufficiently long time and sufficiently many communication channel uses, then we can send the data almost without any error, and the rate would be indicated by the channel capacity. So of course, this assumption are not what we can find in ultra reliable low latency communication, because we do not have sufficiently long time and sufficiently many communication channel uses. So we cannot stay in this asymptotic regime if we are going to study URLLC. Then we require to transit to the finite blockers regime, which says that, okay, so we are not going to assume that we have unlimited number of channel uses. We say that for a specific number of channel uses, which we show it here by n, what would be the efficient rate that we can have conditioning on satisfying the error probability to be equal to epsilon. So for instance, here in this plot, you can see these different red lines are for different number of channel uses. And you see if we want to have the error probability to be equal to epsilon, then regarding the number of channel uses, we will have different optimal rate for our scenarios. So the work of finite block length was again very a top hot topic after a group of researchers in Princeton started to work at it and published this paper. But the problem, not the problem, but the issue, they provide different kind of bounds for different networks on the error probability and also on the rate. But all of these bounds are applicable to the scenarios where the packet is available at the transmitter before the actual transmission starts. And also all the receiver will decode at the same time. So which is we are going to look at the scenario that we do not have these two assumptions. So before I explain the coding scheme that we have, I will go quickly through two of related works on heterogeneous decoding deadlines. The first one considers a broadcast scenario where the sender transmits a single message to multiple receivers, and each receiver has a decoding deadline that is independent from the others. The second work that is a very recent work by Langberg and Efros tries to extend this static broadcasting idea of the first paper to a scenario where there are more than one transmitter and one receiver. So there are many transmitters and many receivers, and each receiver has a different decoding deadline for its desired messages. So the second one considers a time, then tries to have a inner bound on the joint time rate region, which seems to be not tight bound, not a tight. So to just be familiar with what kind of system model we might have through this, this type of work, I will just quickly explain the system model of these two work. I start with the static broadcasting, the first work. They say, okay, we have a single source, is communicating with the receivers over discrete numerical channels. It sends one message to all of them, but each receiver will decode the message after a specific number of channel uses. For instance, receiver one after N1 channel uses will decode, receiver two after N2 channel uses, and so on and so forth. The second work that was on the joint time rate region says, okay, we have many, we have more than one transmitter. We have L communication nodes that are communicating over a discrete memorialized communication channel. And some of the receivers have different decoding deadlines. So they use, they drive an inner bound on the time rate region, which is based on message partitioning and time expansion techniques. So what are these techniques? I will explain it through one example. Assume we have 3 receiving nodes and 1 message. So there is a transmitter that sends this message to these 3 nodes. The first node has to decode this message by a time that is shown by sigma 11 times n. But the second node has a longer time to decode this message, which is by the time sigma 12 times n. The second node really does not need to decode this message, but gets part of it in order to keep it for the future communication as a side information. So now their scenario, their scheme is that they partition this message M1 into 6 sub-messages. Then they will say, okay, we have now 2 different deadlines. One is for the first node, second one is for the second node. The first node has to decode all the 6 sub-messages by the first deadline, but the second node can decode half of them by the first deadline and the other half by the second deadline. And the third node doesn't need to decode all of them, but just decodes 2 of the sub-messages by each deadline. And then this is the message partitioning. And what is the time expansion technique here is that, okay, instead of considering that we have one network, here we assume that we have 2 networks. The first network starts from time 0 until the first deadline, and the second network starts from the first deadline until the second deadline. The point about each of these sub-networks is that the decoding of all the nodes are at the same time. However, they are decoding different parts of the message, but they are all decoding at the same time. And as I said, we have bounds to characterize the rate region and error probability and others for the scenarios that the decoding deadline is same for all the receivers. So then they can, they derive the inner bound, which is also they prove it that is not optimum. So now what is the problem setup that we have here? First of all, the previous work, they all considered that they have only heterogeneous decoding deadline. We also have this assumption that the arrival times also might be different. So we are considering here a scenario of point-to-point memoryless channel with 2 packets. The idea is that at the first, at the time equal to A1, message 1 arrives. So here, as I should emphasize again, that the concept of time is the number of channel uses. So it's here is that at the 8th channel use, the first message arrives. Then the source will encode it, or will send it over the channel. And at the time t equal to A2, the second message arrives. And the source jointly encode both of them, and then we'll send it to the receiver. And then at time t equal to D1, it's the time that the receiver has to decode message 1. So there is decoding deadline. So message 1 is going to be decoded by the receiver, but still we have not yet received the decoding deadline of the second message. So it's going to be sent through the channel until its decoding time arrives, which is at time equal to D2. So this is the setup that we consider. And now how we are going to find the bounds on the error probability of message M1 and message M2 is that we consider here that we have 3 different categories, 3 different situations. The first one is from time A1 to time A2 that we have N1 channel uses. We only transmit message M1. From the time A2 to T1, we are transmitting both message M1 and message M2. And from the time D1 to D2, we are transmitting only message M2. So now how we are going to consider, we say, okay, we have 3 parallel channels here. Each of NY channel uses for I between 1, 2, 3, and 1, 2, and 3. For each of these channels, we have a power constraint that has to be satisfied. And the channels are considered to be Gaussian, which with a Gaussian noise with 0 mean and variance sigma i2. Over the second channel, we have to be careful because we are transmitting both messages. So we use a power sharing scheme where we divide the amount of power that we have for second channel between these 2 transmission. So then we define a power sharing parameter beta. And then we say beta times P2 of the power goes for transmission of the first message, and 1 minus beta times P2 goes for transmission of the second message. And then we define the error probability of the first message by epsilon1 and the error probability of the second message by epsilon2. And the focus is that if we can find a trade-off between the size of the message set, the error probability is epsilon1 and epsilon2, and the decoding deadlines D1 and D2 that we have in a power sharing scheme. So as a result, we can define our region as follows. We say we have the transmit powers P1, P2, P3 is given to us. And then we say a tuple A1, A2, D1, D2, M, epsilon1, epsilon2 is achievable if messages M1 and 2 of cardinality M arriving at the A1s and A2s channel uses can be decoded by the D1s and D2s channel uses with an average probability of error not exceeding epsilon1 and epsilon2. So that is the definition of the region. So what are our results? The first result is a converse bound. So the converse bound here is that we have an inner bound on the error probability of both messages. And with the meaning of the converse is that you cannot have something, a coding scheme that you can have an error probability lower than this bound. Then we have also an achievability based on a random coding scheme, which we can prove that for certain parameters, these two match, and as a result, we can characterize the error probability region for epsilon1 and epsilon2. So how is the coding scheme that is working here, we are using here is as follows. So we said that we have 3 parallel channels. And the formulation is based on standard Laplace transform properties that you can see some details and some more tools in this paper. So the idea is that when we want to evaluate the error probability on the first message, we consider the first channel and the second channel. So we have 2 parallel channels here. And then we say, while we are decoding the first message, in the second channel, the transmission of the second message M2 is going to be considered as interference, to which their SNR or signal to interference noise ratio would be like this. For the first channel, we do not have any interference. For second channel, we have the interference. While decoding M2, we are considering the second channel and the third channel. And the point here is that since M1 already has been decoded by the end of the second channel, we can consider that the M1 is going to be successfully, its interference is going to be successfully canceled for the decoding of M2. Then the SNR for these 2 channels also will have this form. So now this parameter beta is a power sharing parameter. So it means that how much power we are going to give to each of these transmissions over the second channel. So we say that we give beta times P2 to the first message and the rest to the second message. So as a result, if we are considering small betas, then the error probability of the first message is going to be higher than the second message. You can see it for beta equal to 0.2. That is the black line, solid line for the first message, and the black dashed line for the second message. Now assume that we are giving beta equal to half, meaning that we give half of the transmit power to each of the messages. still the error probability of the first message is higher than the second message. And the reason is that because we are considering the transmission of the second message as interference for the first one, but the transmission of the first one for the second one is successfully cancels and there is no interference there. Now the question is that, can I find some kind of beta that, we can have the same or almost same amount of error probability for each message? And the answer is yes, you have to play with the simulation results. For instance, here for this scenario, if we pick beta equal to 0.65, we can have almost same error probability for both messages. Now we say, okay, this is the power sharing scheme that we have. What if we use time sharing scheme? That is a standard way to do it. So in time sharing scheme, they say, okay, over the second channel, if I have in two channel uses, I will say I will divide it by half, give half of it to the first one, the rest to the second. So then they won't have any, we do not need to send them jointly, and each of them will have specific number of channel users and their transmission would be independent. But you can see here, the result for the time sharing compared to the RS scheme that is based on power sharing shows that whenever the power is small, so they are almost more or less the same, but when power increases, the power sharing scheme performs much, much better than the time sharing. Now the question is that I said that for the converse, we cannot do better than a converse, or we cannot come lower than the converse bound in terms of error probability. But the converse that I explained was based on the fact that the interference is Gaussian. So what if the interference is not Gaussian? So the answer is to mathematically consider an interference that is random and has no, it is not Gaussian, is not very easy. So what we did is that we consider that is not Gaussian and is has a random distribution, but it's under the condition that satisfies the transmit power. So it's on the power shelf. And we saw the result and we saw that, okay, they are almost, the same. And as a result, the converse that is based on the interference, which is Gaussian here, is a good converse. So the result can be applied to other scenarios. So for those who are a little bit, like to see how the proof of such bounds work, I will just explain quickly some steps in the achievability proof, which is based on random coding union bound. So the idea is that you have to define a metric, which in this case is this one, the Q, which is the information density of the first channel and the second channel. I'm talking about error probability over the first message. So then we have a maximum likelihood decoder says that given the channel outputs, the decoder selects the message M1 such that this metric for message M1 is larger than all the other messages. And then you can bound the error probability based on this idea and then say it would be expected value of this term, which is based on finding another message that its metric is larger than M1. So to prove this bound, there are some steps. We say that, okay, the first is that we have to find we have to define typical channel output sets, meaning that there are outputs satisfy this condition, which is based on the transmit power of the first and the second channels and the variance of the noise. So the norm of the outputs of the first and the second channel should satisfy this. And by some math work, you can find the probability that the outputs are in this set can be bounded by this set. Then if you have outputs that are typical, then you have to find the probability of having another message that its metric is larger than the message M1. So to do that, let's just define it by a simpler term, saying that G is a function of T, Y1, and Y2, which shows the probability that the metric of another message is larger than a parameter T, given that Y1 and Y2 are in the typical sense. So we can prove that it can be bounded again like this, and it's based on the transmit powers, the number of channel uses, and some other variables, which you can see the details in the paper. And then based on these two steps, we simplify a little bit the bounds that we had. So at the end, we get to this term, which we already know everything, how to calculate, except this probability, which is the probability that the metric is smaller than a term, which to do that, first we assume that we have outputs that are capacity achieving. Then we can bound any the PDF of any output with these outputs that are capacity achieving. And then as a result, this probability can be bounded by this one. And by doing some maths, we get to the probability that this term is larger than a parameter, which these V1 and V2 are non-central k-squared variables. So we are dealing here with the sum of weighted non-central k-squared variables that we call it by Q1. And this is equivalent to the 1 minus the CDF of this variable, which for this we can, we have some papers, including this one, to calculate this CDF. So that's the end of my talk, and I'm going to just conclude it that we have considered a scenario that was point-to-point, where we had two messages with different arrival times and different decoding deadlines. And we derived inner bound and outer bounds on the error probability. And we proposed the proposed power sharing scheme that we had here showed that it's much better than the time sharing schemes, especially when we have high power. And for the future work, we would like to look at the scenario where we have more than 2 packets, of course, and the random arrivals of the packets are, and the arrivals of the packets are random, and they are unknown to the sender. Of course, the other scenarios like broadcast, multiple access channels, and other multi-user scenarios are also of interest. So this is the paper if you would like to look at it, and I'm here to answer your questions.
Thank you, Homa. Daniel?
Homa, thank you very much. Very interesting talk. My question is regarding the overall context. You are supposing that all the packets you want to transmit over the whole capacity have this specific real-time constraints.
Yes.
If you look at the global network, you will have a different type of traffics, and at least for the time being, this specific type of traffic will be a minority. So if you suppose that in the network, we are giving to this specific type of traffic a strict priority, the capacity they will see is huge. And maybe we don't have to solve this problem with a complex coding, right?
Okay.
And I mean, I perfectly understand what you're doing, and it's very interesting because at the end of the day, we will need these type of things. I'm just thinking in the very short term, whether this couldn't be solved just by providing to these packets a strict priority.
Sorry, I didn't hear the last sentence that you said. Can you just rephrase that?
You can understand globally the value, the important value of the work for the mid-long term. I was just thinking in the short term, whether to provide strict priority to these packets, which represent a minority of the global traffic, won't be enough. Because
I don't.
With a strict priority, we will see a huge capacity, being a minority of the global traffic.
So yes, but if you're so you're saying that URLLC packets are going to be minority and the others are going to be majorities here?
Like, yes, you will mix this on the same network.
Oh, okay. So
the same network will transport these packets together with the video packets, which represent today more than, compared with these packets, I mean, 99% of the total, right?
Yes, but their function is quite also critical because they can be thought as data for control applications and so on and so forth, that you really need to have small packages that are going to be transmitted quickly to just get a reaction. So I believe that they are of importance.
I perfectly understand the problem. Again, my point is that let us suppose that your network is empty, and that and you just need to transmit this packet, which represents totally 10% of the capacity of the network, let's say. So in this case, you don't need such a complex solution to reach the error probability you are targeting, right?
Yes.
So now, if you have a network that is not underloaded, but you give to these packets a strict priority against video, for example, those packets will see the network as being empty. Right?
Yes.
And then you can reach the top without this type of solution. So what do you think? Again, I perfectly understand the value of what you are doing for the midterm. I'm just thinking.
I think that is based on the application that you're, for your scenario, maybe we do not need really to go through this kind of problems that needs a lot of math and, you know, a lot of bonding error probability for a traffic that is going to be very, very small percentage of full network capacity and stuff like that. So I agree with you. So we have to just see what kind of scenario we are looking at it. So for the scenario that I'm looking at is ultra reliable low latency communication, that we really consider that there exists such packets and they are of importance.
And they are not the minority of the total traffic, right?
Yes, so they are not.
They are mainly the whole traffic. And just to complement my question, what I said is for the global internet, let's say, but if we talk about the industrial 5G, the things that are going already on in Germany, for example, where the companies are deploying their own 5G network, then in this case, I think the solution is more than relevant. And things like this come also to France, we hope.
Yes, I agree.
Short term. So maybe this would be the scenario on which, for the short term, what you're doing is very, very relevant. The industrial 5G application.
Yes.
Thank you.
Thank you.
Thank you for the talk. I have a question on the way you are evaluating the regions. So for the first message, you consider the psychological interference. For the second one, you remove the first message because suppose you got it right. So do you consider also this epsilon 1 probability of error when the message that you thought you decoded right is actually wrong?
So which message is known? Sorry, it's a little bit foreign.
When you decode the channel uses N2 and N3, you are removing N1 because you suppose you know N1, right? Yes,
so you're saying that if we know also M2 while encoding M1, because here we do not know.
No, what I mean is that there is a epsilon 1 fraction of the time where your estimation of M1 is wrong. And what happens in decoding M2 in the fraction of time? Maybe it's not relevant. Maybe, I don't know.
So I still can't hear your question very well. So you're saying that in N1, we have only message 1, and N2, we have both messages.
Yes, but when, should I get closer to them? I'm not sure. It's very simple. When you decode M1, M2 is treated as interference.
Yeah, it's considered as interference.
Then when you decode M2, M1 is considered as known.
Yes, because it has been already decoded.
But sometimes epsilon1 fraction of the time, your decoding of M1 is false.
It's worse. Yes, if
it's wrong.
Yeah.
Yeah, it's your probability of error. So do you account for that when you decode M2?
So why it's worse?
No, I don't seem to be able to.
So is it clear why it's worse than M2?
No, this is clear. My question is on the previous slide, the one that you were showing before. So in the right box, you say that M1 is already decoded. Okay, so you see, if it's not decoded, then what would be the scenario? What happens when it's not decoded? Do you need to account for that case? Because it will happen. So it's the case that we have a decoding deadline for M2 that is longer or after M1. So I believe that you're saying if we have also, no, not this the case, and the decoding deadline for M1 is after M2. So while decoding M2, we still have M1. So that would be the case again, that we have to consider M1 while decoding M2 also as interference. We can also use some techniques like dirty paper coding and stuff like that to just cancel the interference at the encoder. But that's our next step. So we do not consider that kind of coding. Okay. Thank you. You're welcome.
Also, could you say a few words on the MAC channel problem?
A problem, what?
The MAC channel. You mentioned the MAC channel in the.
Yeah, in the. So we are not sure yet how we're going to deal with the multiple access channels. So there it would be, we have two transmitters. Each of them are sending messages that are going to be with different decoding deadline and with different arrivals. So then it would be a time that receiver is going to have both of them or have only one of them, or the same kind of scenario, but we already really do not know what is going to be the bounds or what are going to be the differences. Because this again will have different channels or different type of states for the messages.
But you need the equivalent of the probability of error for short block sizes, right? So for the MAC channel, so which so that's machinery will rely on tools of this nature.
Mm-hmm. Exactly.
Thank you for the very good talk. I'm sorry I missed the first few minutes. I have two questions.
Sure.
One is how far you consider your work connected with what we call downlink NOMA, non-orthogonal multiple access, and what will happen if we are considering not 2 but 3 or 4 messages? That is the first question.
Sorry, I did not get the second question.
So the first question is how far.
So how we can consider it as NOMA?
And what will happen if the number of messages we are considering is not 2, but 3 or 4?
Okay, so yes, to answer your second question first, because so if we have more than 2 packets, so the scenario would be we have different overlapping times. So then again, we'll have some time that, for instance, we are sending 2 packets, sometimes we are sending 3 packets, sometimes we are sending 4 packets, depending on the arrivals of the packets. So then we will have different type of channels where in each of them, for instance, we have 3 messages that are jointly encoded. In some, we have 4 or 5 or other numbers. So the idea would be then we have to assign the power according to the number of the messages that we have in each channel.
Okay.
So for the non-orthogonal, so I think because it can be, the scenario can be also considered or be modified for NOMA scenarios. So I think that should be also possible.
Okay. Then the second question I had was this value of beta equal to 0.65.
Yes.
Is there a theoretical justification behind this, or it's just by hit and trial that you arrived at this value?
Yeah, unfortunately, we can't just mathematically prove that what is the optimal beta for our bounds because it's very complex. So these are the result of simulation. So we run it for many different betas and then see which one is the one that we are looking for.
I'm sorry to bother you like that, but I guess we have, when we try to connect this to decoding theory in general, you know, the block length comes into picture to find out what is the efficiency of the code and error correcting code that we are utilizing. For example, I think for getting good gain out of codes like LDPC and all that, we have to have a block that's fairly long, which is like 1,000 and so on. So
also, I agree.
Yeah.
Yeah, also LDPC codes and polar codes, they are, one of the solutions that you can use in this kind of scenarios that we are interested in to look those codes also to see if we can use them here instead of random coding scheme that we have.
Thank you.
Other questions in the room? Are there some questions in the bridge? No questions, so thanks again.
Thank you very much. Have a good afternoon.